Hi everyone and welcome back to the channel. Today, we're diving into the world of machine learning operations, also known as MLOps, and a fascinating research paper exploring how large language models, or LLMs, can automate code adaptation within this domain. If you're new to MLOps, don't worry, we'll break it down together. MLOps essentially deals with the life cycle of machine learning models. Imagine you've built a powerful AI model to predict customer churn. MLOps takes care of everything from training and testing that model to deploying it in a way that helps your business. It ensures the model runs smoothly, integrates with existing systems, and delivers real-world value. Repetitive tasks like data version control, hyperparameter tuning, and experiment tracking are all part of the MLOps toolbox. The research paper we'll explore today is titled Automating Code Adaptation for MLOps with Large Language Models. If you're interested in delving deeper, I'll leave the link in the description below. So why is this research necessary? Well, MLOps can involve a lot of repetitive tasks, like adapting code for different functionalities. Let's say you've built a model to classify images. Initially, the code might focus on training and evaluating the model's accuracy. However, to use this model in an application, you might need to adapt the code to integrate it with a website or mobile app. This adaptation process can be time-consuming and error-prone, especially for data scientists who might prefer focusing on the core logic of the model itself. That's where LLMs come in. These are powerful AI models trained on massive amounts of text data encompassing code repositories, programming manuals, and even research papers. This vast training allows them to understand human language and grasp the nuances of programming languages and their functionalities. LLMs can generate human-quality text, translate languages, write creative content, and even adapt code. The authors of this paper hypothesize that LLMs can be leveraged to automate code adaptation in MLOps, streamlining the process and freeing up valuable time for data scientists. To test this hypothesis, they compared the performance of two different LLMs on various MLOps code adaptation tasks. Now let's get into the nitty-gritty of the experiments. The researchers designed a series of tests that went beyond simply modifying code. They wanted to see if LLMs could understand the underlying functionalities and adapt the code accordingly. Imagine you have code designed to track the performance of different machine learning models during training. The LLM might be instructed to modify this code to integrate experiment tracking functionalities provided by a library like MLflow. Here, the LLM would need to understand the purpose of the original code and the functionalities offered by MLflow and then adapt the code to integrate the two seamlessly. One exciting aspect of the experiment involved a task called inlining. In MLOps, inlining refers to incorporating specific functionalities directly into the code rather than relying on separate libraries. The researchers gave the LLMs code snippets that relied on external libraries and challenged them to rewrite the code to achieve the same functionality without those libraries. This complex task requires a deep understanding of the original code and the desired MLOps functionality. The researchers then evaluated the quality of the adapted code produced by each LLM. Here's where it gets interesting. The results showed that in most tasks, one particular LLM, GPT-3.5 Turbo, significantly outperformed the other LLM, WizardCoder. This suggests that GUT 3.5 Turbo has a superior grasp of MLOps concepts and the underlying programming languages. It could effectively analyze the original code, understand its purpose, and then adapt it to incorporate the desired MLOps functionalities, even when those functionalities involve replacing external libraries with inlined code. Overall, this research is a promising step towards automating code adaptation in MLOps using LLMs. Streamlining these tasks through AI could significantly improve the efficiency and productivity of data science teams. Imagine data scientists being able to focus on the core logic and development of their models. At the same time, LLMs handle the repetitive tasks of code adaptation for different MLOps functionalities, including inlining and integration with various libraries. Of course, there's still more work to be done. Future research could explore how LLMs can be further fine-tuned for specific MLOps tasks. Imagine an LLM trained explicitly on a massive dataset of MLOps code and best practices. This could allow LLMs to adapt code, suggest optimal configurations for different functionalities, and identify potential issues within the code itself. Additionally, researchers could explore integrating LLMs into existing MLOps pipelines, creating a seamless workflow where code adaptation happens automatically as part of the model development process. But one thing is sure, LLMs have immense potential to revolutionize MLOps by automating repetitive tasks and empowering data scientists to focus on higher-level challenges. Imagine a future where data scientists can spend less time adapting code and more time pushing the boundaries of machine learning and artificial intelligence. This could lead to faster development cycles, more innovative models, and ultimately, a more significant impact of AI across various industries. However, it's important to acknowledge this research's limitations and the challenges ahead. Firstly, the current capabilities of LLMs might not be able to be generalized perfectly to all MLOps scenarios. MLOps workflows can be quite complex and involve specific domain knowledge. LLMs might struggle with tasks that require a deep understanding of the business problem or industry the model is designed for. Secondly, the safety and security of the code adapted by LLMs need careful consideration. While the research focused on functional adaptation, malicious actors could exploit LLMs to introduce vulnerabilities into code. Robust testing and validation processes will be crucial to ensure the reliability and security of LLM-adapted code in production environments. Thirdly, ethical considerations around bias in LLMs need to be addressed. LLMs trained on vast amounts of data can inherit biases present in that data. These biases could be reflected in the code they generate, potentially leading to discriminatory or unfair outcomes. Mitigating bias in LLMs and ensuring fairness in their outputs will be essential for responsible adoption in MLOps workflows. Despite these challenges, the potential benefits of LLM-powered code adaptation in MLOps are significant. As LLMs continue to evolve and become more sophisticated, we can expect them to play an increasingly important role in streamlining MLOps processes. This, combined with advancements in areas like bias mitigation and security, paves the way for a future where data science teams can focus on innovation and unlock the full potential of machine learning for real-world applications. If you're interested in learning more about MLOps, LLMs, or this research, feel free to comment below. Don't forget to like this video if you found it informative, and subscribe to the channel for more exciting explorations into AI and machine learning.